Hello students, welcome back to the lectures. In the last lecture, I started discussing about application of steady state fluorescence, and in this lecture again I will continue with this. We were discussing in the last lecture how to know the thermodynamic parameter of conformational change. I started with a protein and I discussed that we can know the delta G for protein stability. Protein stability is basically looked at by looking at the conformational change from native state to denatured state or unfolded state. So, this is the equilibria which we were discussing about, and if the delta G for this process is negative, then this process will be spontaneous and protein will be unstable, because it is going from native to unfolded form. When delta G is positive, it means the process is non-spontaneous, and that will tell you that N is more stable than U. N form of the protein is more stable than U, and thus protein is stable. Although I am discussing about the native to unfolded state equilibrium, but you can think of several different kind of equilibria where one form changes to another form. For example, you can discuss about cis trans isomerism, you can discuss about ring flipping. For example, you are going from one conformation to another conformation of cyclohexane, from chair to boat or boat to chair. Similarly, we can discuss about suppose keto-enol tautomerism, that is again two different forms of a same compound, So, when you are trying to look at thermodynamics, you are basically looking at how one conformation is more prevalent than other conformation under certain set of conditions. So, that is what we do when we are looking at the protein stability. We are looking at the conformational change from native to unfolded. We calculate delta G under particular condition, and if delta G is negative, it means the reaction is spontaneous, unfolded form is more stable, whereas if delta G is positive, it means native state is more stable. Generally, to do this, we calculate the value of K first, and as you know that K is equal to U by N for this process. K is equal to concentration of U by concentration of N, and that can also be written as fraction of unfolded form by fraction of native form, and this is related to your spectroscopic signal, and that is what we discussed in the last lecture, spectroscopic signal. So, just by measuring the total fluorescence intensity, look here I am not talking about intensity due to unfolded form or native form, we related total fluorescence intensity to the ratio of fraction of unfolded form and fraction of native form. When we calculated this ratio and related to K, we can express the total signal, total fluorescence signal or total signal due to any spectroscopic quantity like absorbance. So, it is not only related to fluorescence, it is also related to signal from total signal from any spectroscopic techniques. So, y at certain temperature means signal at certain temperature is equal to y due to native form plus y d multiplied by exponential minus delta g by r t divided by 1 plus exponential minus delta g by r t. Here we mean by delta g naught. And so, your fluorescence intensity can be related to delta g of the process, delta g of this process, conformational change process. So, if you experimentally obtain profile of fluorescence signal with temperature, you can fit this profile with this equation, and that will give you value of delta G naught. You can also get the value of delta H m, delta C p and T m, since delta G is related to this whole quantity which I discussed last time. So, not only you can calculate delta G naught, you can also know delta H m, T m, delta C p and delta C p. So, all these quantity can be calculated at a particular temperature just by nonlinear fitting of this profile. We know delta G, we know delta H m, and so we can calculate delta H at certain temperature because we also know delta C p. So, by using Kirchhoff equation and putting the value of delta H m and delta C p, we can get the value of delta H as at a given temperature. We already know delta G at certain temperature T. So, now we have delta G at a given temperature, delta H at given temperature. So, we can know delta S of given temperature, and so we can tell whether this process N to U, if it is spontaneous, whether it is driven by entropy or if whether it is driven by delta H, it is driven by enthalpy. We also need to know that y n is also dependent on temperature, y n and y d is also dependent on temperature. So, we cannot put simply y n at certain temperature here, because y n will change for each value of t, and that is given by this equation. Y n at certain temperature is equal to y n naught plus m n delta t. And if you put in this equation, you can have y n naught plus m n delta t plus y d naught plus m d delta t exponential minus delta g by r t 1 plus exponential minus delta g by r t, and this is equal to y t. And when you are trying to do nonlinear fitting, you must keep this thing in mind, and when you do that, you can get the value of different thermodynamic parameter. So, there are some protein for which thermodynamic parameter has been reported. Our lab has already reported for certain proteins. So, these are the few proteins: trypsin, chymotrypsin, lysozyme, cytochrome C, and the thermodynamic parameter has been obtained for trypsin at pH 3, for chymotrypsin at pH 4, for lysozyme at pH 5 and 0.5 molar Ki, and for cytochrome C it is taken at pH 4. And the thermodynamic parameter here is obtained using fluorescence spectroscopy. Thermodynamic parameter has been obtained using spectroscopy. You can also get the thermodynamic parameter using differential scanning calorimeter, but most of the time differential scanning calorimeter is not available in the lab. So, people depend on fluorescence spectroscopy, and here what we do is we excite this protein at different lambda max value, and that you can know by taking simple fluorescence spectra, and this is the Tm value, this is delta Hm value, and this is the one obtained from calorimeter. These are the Tm and delta Hm obtained from the calorimeter. So, we can know the value of Tm and delta Hm using fluorescence spectroscopy. You can see that Tm obtained by fluorescence is quite close to the Tm obtained by calorimeter DSC technique. Here you can again see chymotrypsin, in this case Tm is 330, whereas in case of DSC it is 331 Kelvin, and this is 350 Kelvin for lysozyme, which is 349.6 using calorimeter. So, you can see that we can almost get quite accurate value of Tm and delta Hm using fluorescence spectroscopy. We do not have to go to a calorimeter. So, one of the important application of fluorescence is to obtain the stability parameter for protein, and similarly you can get the conformational change constant, or you can say equilibrium constant for conformational change, whether you are looking for cis trans isomerism, whether you are looking for keto to enol transformation. We can get the value of K, which is equilibrium constant for that conformational change, and if we measure the K as a function of temperature, we can get the value of delta H, and once we have delta G and delta H, we can know delta S value. So, fluorescence is not only used to know the protein stability or delta G naught value for any conformational change, it can also tell you about effect of different conditions, different additives on that conformational change. For example, generally protein need to be stabilized, for its longer shelf life, and so people use additive to increase the stability of protein, and for that they do some studies, thermal stability, and try to look at how those additive can stabilize the protein. So, for that we can either try chemical denaturation, and again we are looking at fraction unfolded versus guanidinium hydrochloride concentration, which is a well known denaturant. You can also look at fluorescence with respect to temperature, and you can see here that this is your protein in buffer, and this is again protein in buffer, this red one is protein in buffer. If I put co-solvent and we see the shift toward right hand side, we know that your protein is more stable under that co-solvent condition, or on the addition of protein gets stabilized on the addition of an additive. So, here you can see that Cm is almost here, it gets increased to this point, and so your protein is more stable, since more amount of denaturant is needed to unfold the protein. Here also you can see that this is the Tm value, and this is the Tm value in presence of co-solvent, and so there is increase in Tm value in presence of co-solvent, and that means you require higher temperature to denature protein or to convert protein from its native form to unfolded form, and that is why we can see that now protein has got stabilized. We can also look at the effect of salt. This is one of the experiment done to look at the effect of salt on thermal stability of a protein called transforming growth factor. The data is obtained at pH 5. What you can see that this is your at 0 molar, and this is at around 500 millimolar. Salt is known to destabilize or stabilize protein, and in this case what you are looking at is Tm is going from this position to this position, and so there is a shift of Tm towards higher temperature on addition of salt. And what does that mean is salt is stabilizing the protein. Salt is stabilizing the protein, and this is your thermodynamic parameter for stability. You can see that once I add salt, your Tm value increasing, we can also get delta Hm value, delta Hm is also increasing, and delta Cp has changed to a certain extent. So, we can know what is the effect of additive on a conformational equilibria by using fluorescence spectroscopy. There is a very important application of fluorescence in calculating binding affinity for a substrate ligand binding, and substrate ligand binding is quite important. For example, if you are looking for a drug, you need to look at how does it binds to its target, how does it bind to its target. Similarly, in biochemistry, we also need to look at protein ligand binding, since protein ligand binding is a very important phenomena uh, in our body. No function in our body is possible without protein ligand binding, and hence it is important to study substrate ligand binding. So, to know how to apply fluorescence to look at protein ligand binding, first we need to understand the basics of binding. Here I will start with protein as substrate, and we will look at protein ligand binding, but this is equally applicable to any substrate binding with a ligand. Now, we will look at the simple process. One protein interacts with one ligand to give you protein ligand complex. There are two ways to denote its binding, substrate binding to ligand. One is by using binding affinity or association constant. Ka will be given by PL divided by P into L. So, this is nothing but equilibrium constant of this process. There is a second way to denote this, but we look at the opposite of the equilibria, PL going to P plus L, and equilibrium constant of this process is known as dissociation constant, and Kd is given by P into L divided by PL, and that is nothing but simply inverse of Ka value, inverse of Ka value. What does that mean is higher affinity is equal to higher Ka value or lower Kd. So, if you get lower Kd, it means substrate has higher affinity for ligand or ligand has higher affinity for substrate. Generally, if you look at unit of this Kd, you will see that this is molar multiplied by molar divided by molar, and so unit is either molar or millimolar or micromolar or nanomolar. So, unit of dissociation constant will be either in molar unit, millimolar, micromolar or nanomolar, whereas unit of Ka is going to be molar inverse or millimolar inverse, micromolar inverse or nanomolar inverse. Since it is easy for us to denote the unit as a molar, millimolar, micromolar or nanomolar. So, generally we take dissociation constant as a measure of protein ligand affinity, but we need to keep in mind that if there is a lower value of Kd, then it means there is a higher affinity of substrate for ligand or. Okay. So, to know this Kd value or Ka value, what we need to do first is to calculate the mole of bound ligand per mole of protein, which is given by this nu value, which is basically fraction of binding on P that are filled by ligand. So, nu is bond protein by total protein. So, you see this is a fraction of bond protein, and that can be written as fraction is equal to bond protein divided by free protein plus bond protein. So, when you add ligand, some of the protein will go to bond state, the remaining protein will be in free state, and so total protein is free protein plus bond protein. So, nu is given by P L, which tells you about the concentration of bond protein divided by P plus P L. P is protein in free state and this P L denotes the protein which is in complex with ligand. Now, if you remember, Ka is equal to P L divided by P into L, and so P L can be written as Ka into P into L, and that is what we are going to do. So, I just plug in this value of P L in this equation, and what we will get is Ka into P into L divided by P plus, again if I put it here, then I will get K into P into L. Now, you can see P is there in every terms in numerator or denominator. So, it will cancel out. So, if I remove all 3 P's, I will get K into L divided by 1 plus K into L, and if I try to write the same equation in terms of K D, what I will get is nu is equal to L divided by K D plus L. So, this is your equation which tells you how the fraction of bond protein is related to K D. Now, if I plot this new value with the value of L, what I am going to get is this kind of equation, and that is not quite surprising, because at higher concentration of ligand, when ligand concentration is in excess, all protein is going to be in the bond state, and so the fraction of bond protein will be equal to 1, and if I take nu is equal to 1 by 2. So, this is for nu is equal to 1. If I take nu is equal to 1 by 2, I just put 1 by 2 is equal to L divided by K D plus L, and so K D to L is equal to K D plus L, and if I take L this side, I get L is equal to K D. What does that mean is K D is equal to ligand concentration when the fraction of bond protein is 0.5, fraction of bond protein is 0.5. And so, K D is the concentration of ligand which saturates half of the total site on protein. But this is not an easy method. Easy method would be to somehow get a straight line which can give the value of K D. So, let us see how to get a straight line to obtain the value of K D, and the plot which we use to get the value of K D is known as SK chart plot. So, this equation we have already obtained, nu is equal to L divided by K D plus L. If you multiply this, nu into L plus nu into K D is equal to L, divide the equation by L into K D, what we will get is, here in this L will cancel out, K D will come at denominator, in this K D will cancel out, L will come at denominator, at this L will cancel out and K D will come in denominator. And if I take nu by K D this side, what I am going to get is nu by L is equal to 1 by K D minus nu by K D. Now, we have a equation where I can plot nu by L versus nu, and I can get a K D from the slope, because this is a equation of a straight line. So, if I plot nu by L versus nu, I will get an equation like this. So, slope will be given by minus 1 by k d, you see here minus 1 by k d, and the intercept will be given by 1 by k d. Basically, slope itself will give you minus 1 by k d. So, if I take inverse of this, I can get this slope, or from the intercept also I can get the value of k d. One thing you need to remember, that plot must be linear for a standard 1:1 interaction. If the plot is not linear, it means 1:1 interaction is not followed, and it means that more than one class of sites are present and there can be problem with the experiment. So, these are few shortcomings, but there are ways to get information for a different kind of model, but this is going to be out of scope for this lecture. So, I will go ahead and discuss another application, but if you want, I have given EduSat lectures on protein ligand binding. Please go to those lectures. You can know if there is more than one site for the ligand, then how to get a sketch chart plot. So, if you look back, what we did, we plotted nu by L versus nu. So, one thing we need to know is nu value, and now what I will show is how to get the value of nu from the spectroscopic signal, for example, from fluorescence. Once I know the nu value, I can just plot nu by L versus nu, and I can get the value of k d for 1:1 interaction. So, experimentally what we do is we take protein and then titrate with it with ligand, and then measure fraction of protein bound to ligand, and then we plot nu by L versus nu. Now, how to know the fraction of bound protein, that is the main question, which is obtained by experimental tools. The detection of complex can be done either through fluorescence or protection assay, and in this lecture we are interested about how to use fluorescence to get the fraction of bound protein. So, this is what I am going to discuss in this slide. So, you can think of that in the cuvette where there is a protein and I started titrating with ligand, the total fluorescence signal is going to come from three different species, one from protein, another from ligand, and the last one from the formed complex between protein and ligand. And again here I will denote Y as a fluorescence signal, and YT means total fluorescence signal. So, it consists of signal from protein, it consists of signal from ligand, it consists of signal from complex, and YP will give you signal from per molar free protein, Okay. So, Yp into concentration of P plus Yl into concentration of L, again Yl is signal from per molar ligand. So, if we take 1 molar ligand in a solution and then measure fluorescence intensity, that will correspond to Yl, and then Ypl is signal from per molar bound protein. So, 1 molar complex will give you signal, and that is equal to Ypl. And so, if we multiply Yp into concentration of P, it means we are talking about total contribution from free protein. Yl into L will give you total concentration from free ligand, and Ypl into Pl will give you total signal from your complex. and YT is total signal due to protein ligand and protein ligand complex. Sometime your signal is only from the bond protein, not from the ligand or not from the free protein at particular lambda max value. It is also important to keep in mind at that particular lambda max value whether there is a signal from free protein or not, ligand, free ligand or not. So, if suppose your complex gives you signal at particular lambda max, whereas other free protein or free ligand gives a signal at a different lambda max value, which is far apart from the lambda max at which complex absorbs or complex fluoresces, and then at that lambda max there is no contribution from free protein or free ligand. In that case, we can take Yp is equal to Yl is equal to 0. So, Yt will only be due to complex. So, what will happen that you will get something like that spectra. So, this is complex started making, and this is your signal Y, and this is your ligand concentration. So, what will happen that it will go and it will be constant, because all of protein has gone to complex, and after that you are just adding only ligand which does not contribute, and so there will be a constant here, and this value is called Y infinity, and Y infinity will be Y PL into PL max. So, this is the maximum amount of PL which can form, and PL max will be equal to total protein concentration, because after that formation when PT is equal to PL max, after that no more complex is getting formed, all the protein has gone to complex form, and so Y infinity is equal to Y PL into PT, and this is your one equation, this is another equation, you just divide these two equations. So, what I am doing is I am dividing this equation by this equation. What I will get is YPL will cancel out, we have PL by PT is equal to YT by Y infinity. So, YT by Y infinity is equal to YPL cancels out. So, PL by PT, and that is what is here. And this is what is your fraction of bond protein. And so, now you know how to calculate fraction of bond protein. Then you go and plot nu by L versus nu, you will get the value of Kd. This is equal to nu. Now, sometime signal is from free and bond protein. Ligand does not have any contribution. In that case, how to calculate the fraction of bond protein. So, Y is equal to, in this case Y is equal to Yp into P plus Ypl into Pl. This is from the protein, this is the signal from protein, this is the signal from complex. Now, what we can do is we can express P as Pt minus Pl. What does that mean is, you know that total protein concentration is equal to free protein plus bond protein. P is either free or in complex form with L. So, this is called free protein and this is called bond protein. So, this free protein is equal to Pt minus Pl, free protein is equal to Pt minus Pl, that is what we have written here. Yp into free protein, which is equal to Pt minus Pl plus Ypl into Pl. Now, if I take Y infinity signal when all protein has gone to complex, then this is your free protein, and so there is, since there is no free protein, we are talking about all protein has gone to complex form, it means there is no free protein, it means there is no contribution from this. So, Y is simply Ypl into Pl max, and we already discussed about PL max is nothing but concentration of total protein, concentration of total protein. And now you can see that y 0, when there is y 0, we can also calculate the value of y 0. Y 0 means you have not added the ligand, when ligand concentration is 0, and in that case your none of the protein has gone to complexes, means all of the protein is in free state, and so there will be no contribution from the complex, because complex has not been formed. All complex is, all signal is due to protein itself, and protein is totally in the free form, and so you can write y 0 is equal to y p into total protein concentration. So, you have three equations. First, what we will do is we calculate y minus y naught. When we do that, so y p into p t, this cancels out, y p into p t cancels out. What is left is P L into y p and P L into y p L. So, P L can be taken as a common, and what is left is y p, y p L, since we are talking about y minus y naught, this cancels out. So, P L if we take, then y p L minus y p. Similarly, we can get y infinity minus y naught, and that is equal to this, that is equal to this. If you can see, this has the same this term, common term. So, if I divide y minus y naught by y infinity minus y naught, I will simply get P L by P t, which is nothing but fraction of bond protein, fraction of bond protein. So, fraction of bond protein is equal to y minus y naught divided by y infinity minus y naught. So, now you can plot nu by L versus nu, and you can get the value of K d. You can get the value of K d. This is the way K d can be determined, or K can be determined using fluorescence spectroscopy. In fact, you can use signal from, you can use any signal from any spectroscopic technique, which gives you, which is basically proportional to the concentration of the fluorophore, concentration of the fluorophore. Here I will show you one result where people have looked at the binding of ANS with bovine serum albumin. They use same equation, y is equal to y max into ANS divided by K d plus ANS, and by just fitting this curve, they obtain the value of K d, which is around 8.63 plus minus 0.29 macromolar. So, we can get the K d value using fluorescence. There is another example where we have looked at how curcumin binds with a protein called superoxide dismutase 1. So, this is your spectra. So, here is curcumin, pure curcumin, and it is now titrated with SOD1. So, what we are looking at, how fluorescence signal from curcumin changes when we add SOD1. And here what we did is, we applied the equation which we derived when we are discussing about static quenching, and in case of a static quenching, we can use Stern-Volmer equation. So, F naught by F is equal to 1 plus Ksb into Q. This is for your collisional quenching. So, just remove this, and there is one modified Stern-Volmer equation. I am not going to discuss that, but that can also be used to get your Ksv. Yeah, here Ksv is basically association constant if we are talking about static quenching. So, quenching can be due to simple collision of SOD1 with curcumin, and second can be due to your complex formation of ground state curcumin with SOD1. So, first we have to look at whether it is a static quenching or dynamic quenching. If it is a static quenching, then we can get the value of Ka. Okay. So, this is the plot F naught by F versus curcumin concentration. If you remember Stern-Volmer plot, so F naught by F versus curcumin, and if I assume that this is a collisional quenching, then we can get the value of Kq, which is higher than maximal collisional quenching constant. So, we get a very high value of Kq, and it means that it is not a case of collisional quenching. Collisional quenching, the value of obtained binding constant indicates moderate binding of curcumin to DTT treated SOD1. What we did is, in this experiment, we first tried to look at whether it is a static quenching or dynamic quenching, and one thing I told you to differentiate between a static and dynamic quenching is measure lifetime in presence of quencher. If lifetime does not change in presence of quencher, it means it is a case of a static quenching, and that is what we did, and what we found is your lifetime of curcumin does not change in presence of SOD1, it means it is a case of your static quenching, and from this plot and slope I can get the value of association constant, association constant or dissociation constant, and what we got in this case is there is a moderate binding of curcumin. The Kd value is in micromolar range, which means it is a moderate kind of binding. Fluorescence can also be used for calculation of kinetic parameters. Kinetic parameters, if you remember kinetic parameter, for measuring rate constant, we utilize the integrated rate law, and this is the rate law for 0 order, this is rate law for first order, this is rate law for second order. And if you look at, we need to measure A value in all these. So, concentration at a given point we need to measure, but it is very difficult to measure A, concentration of A at particular point in the reaction, or during, if we are looking at reaction with temperature, it is very difficult to measure concentration of a particular species at a given point. So, what we generally do, again we take help of a spectroscopy to measure concentration, or particularly measure concentration ratio, and I will show you how by measuring total spectroscopic signal you can get the ratio of concentration, and that can be used to calculate the value of rate constant. For example, take a simple case, A going to P, A is a reactant, P is a product. At time t, we started with A mole and P is 0. At time t, it is A minus x, so x will be the product, and t is equal to infinity, A goes to 0 and product will be A. Now, think of the spectroscopic signal. A spectroscopic signal will be given by Ka into A, where Ka is a spectroscopic signal due to 1 mole of A. So, Yt will be K1 into A minus x plus K2 into x, and K2 is your small K2 is your spectroscopic signal due to 1 mole of P, 1 mole of P, and this is a spectroscopic signal per mole of A. So, total spectroscopic signal at time t will be K1 multiplied by A minus x plus K2 multiplied by x and when t is equal to infinity, your signal will be only due to product, and so y infinity will be k 2 into a. So, now we have 3 signals at 3 different points. So, now let us do y t minus y infinity. If you do that, you will get k 1 minus k 2 into a minus x, and if you do y 0 minus infinity, you can get k 1 minus k 2 into a. And so, if I divide y t minus y infinity by y 0 minus y infinity, I will get a minus x by a. So, the concentration ratio of A at 2 different time, at time t is equal to 0 and time t, can be obtained by measuring fluorescence intensity at different point. You can try of different reaction, for example, A going to B plus C, same thing will be obtained, you can try yourself at home, but what we need to know that a minus x by a is equal to y t minus y infinity by y 0 minus y infinity. So, now we can write first order equations. First order equation is what? Log a naught by a is equal to log a by a minus x is equal to k t. And we have already calculated this ratio. I wrote a minus a by a, but you can write also a by a minus x, and that is equal to y 0 minus y infinity by y t minus y infinity. And so, now you see I do not need this, just by having the your signal, spectroscopic signal, in this case fluorescence at different time, I can know this ratio, and now I can plot simply log y t minus y infinity versus t to get the value of k, rate constant. For a second order equation, we know this is integrated rate law. What we need to do is, we need to express this equation as a ratio of a by a naught or a naught by a. The way we can do is, just multiply this whole equation by a naught. So, we will get a naught by a minus a naught by a naught, which is 1, is equal to k t into a naught. A naught we generally know, our problem is to measure a at different time during the reaction. So, we can write a naught by a is equal to k t a naught plus 1, and this already we have calculated in the earlier slide, and that is equal to y 0 minus y infinity by y t minus y infinity, and that is k t a naught plus 1. So, now we can just plot y t minus y infinity or y 0 minus y infinity by y t minus y infinity versus t to get the value of k. So, a spectroscopic signal not only gives us a tool to measure delta G, K, delta H or delta S, it also gives us a tool to measure the kinetic parameters. So, I will stop here and thank you very much. Next time we will discuss the time resolved spectroscopy. These are the some references. So, thank you.